unit shear strain. Of course, you should have learned this from the first courses of structures. So in which case you have, so if this is your structure, if this is your structure, then, and however you load it, so here we have a force and a okay, usually there's a moment, but because of the edge condition there is no uh, moment at the end, but somewhere there's a, so for example this uh, st- uh, structure will deform as shown. So when it deforms here, there is some theta, there is some theta, and that is caused by the moment. All right, and so forces. So the point is forces cause displacement, moments cause unit rotation, and torsion cause shear strain. That's the first thing you need to know. Now uh, this this I mean the stiffness matrix. Stiffness is defined as, for a force is a amount of force that can cause a unit displacement. For a moment is amount of moment that can cause unit rotation. For torsion is amount of torque that can cause a unit shear strain. That's the point. Now, all these things, if all these things are available in a stiffness matrix, the force, the vertical, you call it shear, moment, and torsion, then in fact the stiffness matrix would be a just a single. For example, this is a now because I need you to see the and I forgot one thing. I think I need to add it here. You'll excuse me, discard. And actually, this is not the everything. For a force, okay, for a force, a unit. Okay, I think it's fine. It's fine. But now you need to there is axial force and vertical force. So it's still okay. Try my best to explain. So if this is your structure, this is your structure. There are 3 degrees of freedom. Not even. I think there are more than three. 4, in fact. 4 degree. You know you're interrupting me. I don't know. I keep going back and deleting what I have drawn because you don't want to keep time. Everyone wants to class rep. This has to be controlled because we seem to be wasting a lot of time. Okay, now the again another one wants to join. Something is wrong. Okay, here now. Uh, so we need a no, no, not a pen. We need a pen. Okay. So if this is your the structure that you're talking about, there are several degrees of freedom. One, there is a shear force, and then there is a moment. It's possible. There is and then it's also possible to have a torque. So it's also possible to the torque and the moment would confuse you a little bit, but please know. So there is the torque. So this is the torque. The yellow one is the torque. This is the vertical shear force. This is the moment, and this is the axial force. So each of these have their own. For example, to get this, if you know this force for equals Ke. This is for axial force. You were taught this. So the extension that we need would be here now. Extension, or E, would be F over A, and this one is EL, is PL over A. If you remember, PL over A. Is it EL something? Yeah, so I'm not sure this is the correct one. Let's see. Yeah, so for the axial force, if we can assume a unit force, a force that can cause unit. So for the axial direction, the stiffness is a force that can cause a unit direction, a unit displacement in the axial direction. For the vertical direction, the stiffness matrix is, or the stiffness is the amount of force that can cause a unit vertical displacement. For the torque, the same. Because torque causes shear strain, amount of torque that can cause torsion, amount of torque that can cause a unit shear strain. For the moment is amount of moment that can cause a unit rotation. That's all. So we have to arrange all this. So you can see from this, from the first end, we have 4 elements. All right, 4 elements. So for the matrix will be, because of this edge alone. So for example, because these are real values, so we can say, and one, we have a matrix, one matrix for the horizontal force. Uh, let's call it H1. But for the, because in that horizontal direction, moments, all those things have nothing. So all these are 0. So 0, 0. Because they are 8, they will be 8 because this is 4. The first end we have 4, and the second end there are 4 as well, the same but in opposite direction. So 1, 2, 3, 4. Then no, at the fourth one, at the fifth one, I believe we'll have negative H, because this would go like this. On the other end, it's the opposite. Yeah, so 0 and again 3 zeros. So for then we go to this the vertical. We have another 8 to the vertical force. So this is for this. This is for the axial direction. This would be for the vertical direction, and this would be for the moment, and the fourth would be for the torque. Then for the other direction, another 4. So this, for this case would have an 8 by 8 matrix. However, you are lucky because most structures do only have shear and moment. Actually, that's the biggest problem. Shear and moment. A few cases you will also find a direct axial force, as you will see. So the matrix, the most complete matrix, if you watch the video, you'll see you have a 16 by 16 matrix. But in fact, in most cases, we don't have torsion because we don't design our structures for torsion. Rarely do we do this, and in any case, the softwares can do this for us. But the most common that you at least have to know is to derive when there is a vertical shear, and also when we have the moment, and sometimes we also have axial forces. So we are going to derive this as we go along, and hopefully you understand. So the what we can do is basically what's important is to know what a node is. So a node basically is the kind of some boundary which are normally denoted by supports or edges. So for this beam, this could be nodes. This is another node. That's another node. It's convenient to take notes at the supports. Or if you have, for example, frame structure. If you have a frame structure, then this is a node, this is a node, this is a node, and that's a node. All right. If you have a overhanging beam, for example, this one, and there's another one there, another one there. Depends on you. You take this as a node, this as a node, and this as an this as a node, and also the free end as a node. So yeah, so these are points that help us break the structures at convenient places so that we are able to derive what we call a stiffness matrix. Uh, because many people think this is difficult, I will try to go a little slowly to make sure you are able to understand and demonstrate with the examples. And so the uh, so I need us to go slowly, yeah, all right. So the first element in whatever orientation, because the stiffness matrix is useful because it will be helpful even uh, even if for example the structure has no orientation, the orientation is not vertical, because these are normally because a structure can be horizontal like that or vertical. So normally we want what we call a global direction. So let me uh, try to have a better explanation for this. For example, if you have, let me try to go back. I think there's enough space to explain. Okay, and how do I clear this? Okay. Let's see. For this structure, for example, the beam. For if you consider members, so let's say A, B, C, and D. If you consider the individual members, the axis direction for this is, let's call this Y, and that is X. And for this member BC, this is Y, and this is X. For member CD, this is Y, and that is X. Excuse me. To get the global stiffness matrix, you have to choose which is the global, because you can see those individual members have their own axis system. So you have to choose what is called global direction, in which if you resolve. So let's say our global direction is this. So it means the only one that conforms to that direction is this. So it means once you derive the stiffness matrix for B member BC, you don't have to transform. For these other ones that are not vertical, are not horizontal, you have to convert. You have to transform. So you find their stiffness matrices, but you have to transform them to the direction, to the global direction. So that's why you see there is what you call a transformation matrix as well. So this was just an example. You see, it's uh, the the structure is not vertical. So if we for this case we have what is called mm, local, because it only refers to the to a separate individual member, because this structure can consist of many. So if this is your structure, many members, your structure. So if you only talking about member AB, that would be called local AB. See. So if you're only talking about member AB, that would be called local stiffness matrix for that member. And that local stiffness matrix doesn't care about the orientation. But now if you transform, taking care of the theta, then the uh, local member stiffness matrix, you have to transform it to conform to the overall direction of the structure. All right. So first of all, we talk about what is called member stiffness matrix. So or local. So this is local. This is called member or local. So so this is just assembly of what you already know. And unless now you did not you did not understand the concept very well. As you can see, for the first member matrix, it's an axial force, and this you already have known from your the actually you know that the is P is called what? Let's see. We can drive this. This is not should not be a very difficult thing. What's happening? Okay. Pen. We need a pen. No, and that color may not be very good, so let's choose a red one or green. Red one. Okay, let's choose a red one. So you know, for example, this common force that we say that the force is equal to, or let's call it P, is equal to KE times the extension KE. All right. But the force, we know that sigma, the stress. Okay, if you check this, mm-hmm. uh, but this force also is equal to the stress times the area. So stress times the area, right? This force is the stress times area. But the stress uh, So the stress, or we know that E is basically change in stress. We can say stress over the strain. So actually the strain is sigma over E. So E sigma A, in fact. So we can say here P is E E E E over A. And this extension, so this we can substitute back there and say AE should be K, but E is measured in terms of L, so KL. So in fact K is equal to, I need you to see how that formula shows up in the stiffness matrix. I'm just trying to explain. Over L. Now the stiffness is when this value is 1. I said a unit displacement is 1. So AE over L, you can see why. So that is the stiffness matrix. So okay, that's the theoretical part. So by the same logic, you can derive all these other stiffness matrices. Okay, so but here now is just to explain the logic, the concept. Excuse me. So for to cause a unit displacement, you need the value AE over L, which I think you've seen how we've derived. So I've said the stiffness matrix is for a force, amount of force that can cause a unit displacement, just one. So in this direction, if you see, and to derive the stiffness matrices, you consider the all the forces that exist one at a time. When you are, for example, in column 1, you are only considering the axial force, this one. If the force is applied axially, the resultant can only be there in an axial direction. It cannot affect any other direction. So for this reason, you can see the first value is AE over L. Then the rest of those values are 0. Then the fourth value now refers to because if this is a positive direction, in the other direction it has to be negative. So you can see. So the first value is A over L. The second one is 0. Third, and the fourth one is the opposite. The rest of those are 0. So that is for the axial force. Now this beam has both axial force, moment, and so axial force, shear force, and moment. So this is for the axial force, the shear force. Now the shear force always will cause a moment. So two columns exist, because when you apply a force, if you apply a force here on the beam, it will cause moment and also cause a shear. So that's why you see, but it doesn't cause anything it doesn't influence anything in the horizontal direction. Remember, this is we are still using the Timoshenko beam theory, if you remember. And Timoshenko beam says that the beam is so thin that the axial forces, the action due to the vertical forces, the axial forces are negligible. So what we are saying here is that the forces in the axial direction do not cannot cause any resultant in the vertical direction, but also that the forces in the vertical direction do, unless the beam is in like, for example, if it is inclined like this and there is a support, then of course due to the inclination there will be a horizontal force, net horizontal force in the beam. But if the beam is just this way, and then you apply a vertical force, that vertical force cannot result into any net horizontal. So this is why you can see the first row here is 0. The second row has to have a value because that's where you apply the vertical force, and the third also has to have a value because the vertical force always causes a moment. And the axial is 0, and this one have some relationship. So because if this is positive, if it's positive in one direction, it has to be negative in the other direction for purposes of equilibrium. And so this is how we drive the second column. Now for the third column, when you apply a moment again, so this is related to that. Now for the third column is related to moment. Again, when you apply a moment, it affects vertical forces as well. So again, you see these two rows have values. Now what you need to care about now, this has to be derived by what we call the what is the slope deflection method. So if you apply if you apply a unit, or if you apply a unit moment, so this is the moment you apply here, it will induce this amount of vertical force, and then the vertical force have some inverse relationship with the because this beam has to remain in equilibrium either way. So this vertical force has to have an equivalent resultant, equal and opposite. Now you remember that for a fixed end moment, if you induce 4EL, it on the free end it will induce half the moment. You can see that. So that's how we arrive with this, how we solve these values. In other words, what I can tell you is these stiffness matrices are derived when you at a time I cannot stress this enough. Hopefully it makes sense to someone. Each degree of freedom, you need to know how many degrees of freedom you have. So each degree of freedom, you apply a unit displacement, ignoring everything else, and then trying to solve the stability of the beam. That's all. So for the I think that's the simplest I can put it. So for the for this layer and this one, you apply a unit displacement there, and then you try to solve for equilibrium. For equilibrium, there has to be another force that balances this. So if this is AE over L, this must be negative AE over L. So you ignore all those other ones because this horizontal force cannot affect the other forces. So that's the first thing. So that's how you can see how these and these are derived. So at a time, again, now when to derive this column, you apply a unit displacement on this end only, and you can see now on this end this would be negative, this would be positive AE over L, and the rest are 0, negative A over L. Now, when it comes to this column 4, again, you ignore everything else and apply a unit negative in the opposite direction. When you apply a unit, this becomes negative A over L. Everything else is 0, and this becomes positive, and that's all. Now, for the column here, you apply, what you apply is this, all right? Uh, for the vertical, all you apply is this is the, so you apply a unit direction in that, a unit displacement in that direction, and you solve. When you apply the unit uh, displacement in that direction, then you realize that is the reaction, and these reactions have to be in equilibrium. So if this direction is positive, this shows a negative value, and then the resultant are those kind of moments. So by applying a unit sorry, no, that's not right. Here, by applying a unit uh, displacement in this direction, it means you apply this amount of force, and that very action induces these moments here and there. So in other words, you can apply this amount of force and try to solve the equilibrium of that beam, uh, considering all you know about in structures. So that's the part, the explanation part. So for this, the second column, you apply, this is what we have applied, the rest are the reactions. For the third column, this is what we have applied. And please note, the green one, not the green, the blue indicates what has been applied, and the rest are a reaction of what has been applied. And please note where and how it has been applied. So for this, the first column is we apply this one, and the rest are reaction, so the rest are 0. For the second one, this is what we have applied. This is what we have, this amount we have applied. The rest are a reaction. For the third one, this is what we have applied. So when we reach the third one, we have exhausted all the degrees of freedom in the first node. Then the fourth one, in the fourth one, you can see now, the fourth one now you can see we are applying the unit displacement in this direction. All right. And now this direction is different, is different from, you can see when you apply here, it causes a negative, because we had assumed the direction, the universal direction is this way. So when it induces some other force in the opposite direction, then this is the same, this for this reason. All right, because when you induce this way for equilibrium, this has to act. So uh, this is the, like, the displacement in this place due to a unit displacement there, the same. So this is more of like we are considering you remember the Maxwell theorem, that if you apply a force here, it will cause a displacement, the same effect in another area. Now for moments and shear forces, they affect two things. Moments affect the degree of freedom of the moment, and also affect the degree of freedom of the shear force. Now the axial force only affect the 1 degree of freedom. Moments and shear force affects 2 degrees of freedom. I think you need to remember that. So once you exhaust the first node, you go to, so this from 4, 5, 6 are dealing with the second node, and I believe I've tried to offer some good explanation. Now, something to note here. Now, if we had torsion as well, so if we had torsion as well, torsion would make would if we had torsion as well, torsion would if we had torsion as well, torsion would come here. Now the fourth, so it would be the fourth one instead of the. So torsion would come here, and torsion would also come here, just before the fourth one. So this is for the first node, and for the second node, torsion would come here, and torsion would also come at the very end. So you can see now we'll have added 2 rows here and 2 columns, and now this for now this is 6 by 6, but if there were torsion, this would be a 8 by 8 matrix. So you can see how these matrices are usually simplified. So because the torsion part is not there, the matrix reduces from an 8 by 8 to 6 by 6. Now, if for example the moment was not there, or the actually this is what is usually not there, the matrix would reduce. So this whatever I'm highlighting would be not be there. So you can see the matrix reduces to a 4 by 4. So I think you need to note that, because many students usually get confused. So that's the first thing to note. The second thing to note is that the the matrix is actually uh, symmetrical about the diagonal. So in fact, so let me tell you what you need, so that you don't get trouble. If you can cram this matrix, cramming is not a good word, but it will help you if you know how to this arrangement. But that's not all, because you need to know when it reduces, when it is 4 by 4, when it expands to 8 by 8. But this is a good start. So when you can know this matrix, then you are sorted in this topic. The trick now, once you know the first three, these ones, they have a relationship with the first four. The first thing I have told you is that it is symmetrical. So if you can figure out, if you can figure out the first three, then you're pretty sorted. For example, you can see the first column and the fourth column have some inverse relationship. So this becomes negative of that, and this becomes negative of that. Here, all these are positive. Now, whatever is positive for the fifth one, whatever is positive in column 2 becomes negative. You can see. But please pay attention. That is not the same relationship with the moment. You can see there's some difference with the moment. So if you know, if for example you have derived the first three and knows the relationship between the fourth one and the first one, the fifth one and the second one, and for some reason you don't know the sixth one, it's very simple to see. This thing is symmetrical at uh, the the symmetrical at the diagonal. So for example, you are stuck, you don't know what the fifth value here is. So you just hold it here. This and this have to be the same. So because you have filled the first half, so and you are here and you are stuck, so this has to mirror. So these values here are the same values there. So if for some reason you don't know column 6, you can easily fill. Again here, these values and those values have to be the same. Again here, this and this, this and this. So that will help you to somehow now the rest is your own way of, if you find another way that will make this easier for you. So this is the first start point, how to understand this stiffness matrix. I'll pause here. Probably people have questions to try to answer to the best of my ability. Questions? Yes? No question so far. Hello? Class rep. People don't have questions, or people are doing their own things. I need some response. Hello? Yeah, is there any question? Okay, so okay, fine. If you're okay, we move on. And so so that's the idea, in fact. And the only other thing you need to know is to transform because of the orientation. Sometimes uh, the beam or the member is not uh, aligned to the universal or what you can call the global stiffness. So you need to know these values, the theta x, theta y, and of course these ones have just the relationship with the sine and cos. So as you can see, this is xj minus xi over L. That is cos, right? That is cos, and this is sine. So to transform this transformation matrix again is very easy. So cos theta, sine theta, negative sine theta, cos theta, and this is 1. Again, this is cos theta, sine theta, negative cos theta. And but now if this angle is the same, because sometimes you might have different angles, but just please note the if at all this is confusing you, this is nothing except uh, this is nothing except cos. So you only need to know the angle cos theta, sine theta, and the rest of those ones are 0, 0, 0. This is negative sine theta, cos theta, 0, 0, 0. And this is 0, 0, 1, and then the rest are 0, 0. Of course, this is if this is a 6 by 6 matrix. Please note that. And the same, this is the same as the same here. So cos theta, cos cos theta, negative sine theta, 0. Okay, it's getting messy, but you get the. I hope you get the idea. So I have to erase. So once you know that, that's all. Okay. Now the arrangement in the how to solve the problem, in fact. So once you get the transformation matrix, which we have talked about, transformation the transformation matrix. So to solve your problem, in fact, okay, I'll cut to the chase. There's those derivations uh, you can see for yourself. But what I'm interested is if you want these forces, the theoretical part, if you want to solve the forces, should be the K. The K, that is what we have said, and K is the now the K has to be. I'll show you how to do that. The K is what you call the global stiffness matrix times the displacements plus the fixed end moments, the fixed end values. So there are standard tables to get this fixed end moments, which you know. K you can get this. Now the issue is here. The displacements based on the support condition. For example, you know that in fixed support, not fixed support, sorry, for a pin end, the moment is 0, and displacement, we cannot have any displacement is 0. So using these boundary conditions, then you're able to solve. I'll demonstrate to you shortly. You're able to solve your problem. I think let me so this is also key. This formula is key, but needs some keen consideration. So you first of all you need to know the what does the boundary condition say, and what do you know. Now this part is also important. If for example you have loads applied at the nodes, for example here, it might be useful. So if you have a load applied directly at the node here, then you put it here. You have to add it here. Now this Q are these are the reactions, for example, the VA here and the moment, for example. So this is what, yeah. So this for a fixed end moment, you don't know the value, so you put them there, and hopefully you are able to solve with this matrix. But if for example there are loads at the nodes which are not support, then again that what this you put in this matrix. So depending on what is available and what is not available, you can isolate a certain part of that matrix and be able to solve quite easily. And here I have to tell you that you have to invest in a good calculator. You should be able to solve, I think, up to 6 by 6 matrix at the very least. And again, you need to isolate. You know how to isolate that you solve. Actually, if you assemble the matrix will look huge, but in fact, if you know how to isolate it to solve, it might not be. So the key is knowing how to isolate. But sometimes it might call that you able to solve a 6 by 6 matrix, which I'm not sure how much maths you know, but you should. There is what there is. Okay, I don't know how much maths you know, but I'd suggest you invest in a good calculator that is able to solve. It should not be programmable though, but you should be able to solve 6 by 6 matrix. In this course, I will teach you with Excel, because Excel by a simple command you're able to solve the stiffness. It doesn't matter the number. Excel can help you solve any amount. But for your exam, because at the end of this you have to do an exam, you should at least know how to solve a 6 by 6 matrix. If you're lucky, I put it 4 by 4, and I don't know how much. There's a method called reduction. I don't know how much reduction can do. It's called whose reduction. How to solve matrix? There's some method there. I'm not sure you can do it manually, but I'd suggest you invest in a good calculator. For classwork, you can use Excel. Now Excel is good even for your work if you graduate after graduation, but for the sake of the exam, at least you need to be able to solve at least a 4 by 4. So this is what I was trying to explain. I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is also missing. This one is making some assumptions, But the complete one, if you are to consider torsion, shear, a moment, you can have I think 1, 2, 3, 4, 5, 6. It says 6 by 6. Anyway, depends on the, I don't know. So the global stiffness matrix can depend on any number of no, okay, this is, sorry, this is still 6 by 6. You can see this is 1. So this 1, 2, 3, 4. So this is only considering the three things. There is not torsion, as you can see. So actually this is okay, this is considering only this. So the three, we are talking about axial force, the shear force, and the moment. If there were torsion, it would be 8 by 8, as I have explained. Don't be intimidated by those many um, symbols. I think it's more important to understand what they mean. So first, this needs to be your friend. So I'm going to try to demonstrate with an example here. I'm not in a hurry to run into the example because I know probably it's uh, okay, might take some time to grasp. But the first thing I have to tell you is these tables have to be your friend, because depending on the arrangement, the load arrangement of the beam that you have been given to solve, you should be able to, depending on the beam arrangement, uh, you should be able to calculate the fixed end values, because in fact you will need them. So these tables should be your friends. These tables, if required in the exam, will be given to you, so no need. You only need to understand the implication, what it means, or how to use them. So these tables, the displacement, these are the tables I was telling you in the previous topic that you need to understand. So if you're supposed to calculate a displacement, you don't need to waste a lot of time. Just know how to substitute in the formula. So I stop here because I think that example is a bit complicated, and go to the. I will stop sharing this one. I will share with you an Excel just to demonstrate how you should be able, how you can solve such a problem. It comes in Excel. You can do this, I think, also in your in your with your uh, calculators. So just to demonstrate how you can solve. So for example, this previous example that we had talked about, and now there is nothing here that you don't know. So this is the. Please confirm that you can see the Excel sheet. Hello. Please confirm that you can see the Excel sheet. Yeah, so this is the stiffness matrix, and for this case, this stiffness matrix is okay, except now we are going to reduce it to 4 by 4 because the axial forces, there are no externally applied axial forces. So we only remain with the 4 by 4 matrix and reduce as I have already indicated to you. So this beam here, the length is 12. So we need to establish the uh, the uh, the fixed end values. For this, you already know the fixed end values. This is at the midpoint. If you check those tables, the fixed end values is PL/8. So you can see the you just put there 50 times 12 divide by 8, which you are able to solve. So in this class, we will assume that the because on that side in the AB, if on the side AB, the first on A, the fixed moment at A, let's assume it to be positive, and on the B side is negative for the purposes of this class, all right? And so the uh, so that's the fixed end, so you need to solve that. And then on the B side is negative, and then the fixed end values, because of the fixed end values, you assume is a simply supported beam. You forget about the fact that it's statically indeterminate. So based on the loading scenario, of course, the VA, this is at the middle, so VA and equal VB, which is 25. So those are the fixed ended values. All right. Now to derive the stiffness matrices, you simply substitute uh, substitute here like shown. So we ignore the axial parts which are not there. So we only end up with a 4 by 4 matrix as shown. So this for example 12 EI over L cubed is this value. So you just 12, you can see EI is factored outside. So 12 divided by the length cubed. All right. And the second value is 6 EI over L squared. You can see we skip that axis is not there, the axial part is not there, so you skip it and then go to negative 12 EI and then to 6 EI and the same. So for the second one, uh, you substitute there, this part is not there, you substitute this, you skip this and that, you substitute this, you skip this and that. So that's how we derive this 4 by 4 matrix. Now for this case, there is no orientation. So this is the same. You don't transform. We don't need any transformation. But for this point, we just have to demonstrate how to solve the or how to assemble. So you remember we said Q matrix. I don't know. Let me try to copy if it makes more sense to you people. The we said here the probably make sense here. So first of all, let's confirm. This is when we have fixed ended moment. This is PL over 8. So that's the first thing you need to confirm. Now the what I did this what I'm looking for. So this in fact uh, the Q. Okay, let me write my own because that seems complicated to me. All I'm interested in is to tell you that the Q matrix, and what that means. I think this is my biggest interest because most students have problems because they don't seem to grasp what these things mean. So the fixed-ended forces, the fixed. I don't want. Okay, let me try again. Erase. Q matrix equals the K matrix, times the displacement matrix plus Q F So what does this mean? No, I realize I cannot write. I cannot copy. Unfortunately, or we keep it. Let's see. Okay, yeah. So let's snip it here and put it so you can see. Snip it here. So I'm starting with. I'm gonna start with a very simple example, as just to demonstrate to you. So let's put this in the Excel so that you grasp what that means. So this is the arrangement. This is what you need, and with physical values. With physical values. So the okay. So the Q matrix means, so this is the meaning. This is actually the arrangement. So this this is the Q matrix, as you can see. This is the stiffness matrix, as you can see, and this is the displacement matrix, and this is the fixed-ended matrix, which you have seen how we and you can see that it's now that what those things means. Now, how are we able to solve this? We're able to solve this based on the end condition. For example, the first on edge A, this is a fixed end. So fixed end, there will be a vertical reaction. Horizontal reaction is not there. That's why we omitted the first column. So there will be a moment and a vertical reaction. So you can see VA and MAB. So the VA is the reaction here and the moment at AB. Now, ideally, at end B, there will be, of course, a VA, the reaction at VBA, and also some moment. But now, this is the key. But we know that this is a pin, so for fixed end, no moment can be zero. The reaction also cannot be zero. But at end B, we know that the at end B, we know that the at end B, in fact, we know that the uh, the moment is zero, but VBA cannot be zero. So this kind of conditions is what we used to solve. And then these are the displacements. What does this mean? VAB, this is a fixed end. We cannot have any displacement unless you are told specifically that we will allow a displacement of 1 millimeter. Then you can put, of course, you have to use standard units depending on the units of your EI. So if you have to put any displacement here, has to be in standard units. But typically for unless the displacement is defined, you assume it is zero. So for this is fixed end, we cannot have any displacement. There cannot be any theta because of the fixed end. Again, for a pin, we cannot unless the displacement is prescribed. So that is 0. However, for the theta is not 0 because there is no moment. If there is no moment, there will be some value theta here. Okay, and of course with a fixed value. So you can see that if you are to solve, we have one equation here that is able to solve this very easy for us, because this MBA, so we can say MBA is 0 equals, which equals, so this times that is 0, this times that is 0, this times that is 0. I hope you know how to use matrices, and that will only tell you that 0.03 equals sorry, okay, equals seems to be messing us up. Escape, can you okay, that equals, then equals now 0.33, now this value 0.3333 of theta BA. This is we can copy here. Okay, I just subscript, this subscript. Okay, good. So 0.33 of theta ABA plus of course negative 75, sorry, negative 75. You can see now you have just one unknown which you can solve. So theta BA would be 75 divided by 0.33 something, right? Sorry, you don't forget to multiply by EI. So actually, in fact, if you had the value of EI, you can solve. Sorry, something is wrong here. Anyway, you should know that this is multiplied by, okay, EI as well. So if you had the value, if you knew exactly what the value of EI is, you should be able to solve the problem basically. So once you solve theta A BA from this equation, then you put here, and now it's very easy. Once you know the value here, VA would be this times that plus this times that plus this times that. The beauty is the first three columns will reduce to 0. The only this one is we're going to have something. So 0, this value times this. Of course, don't forget to multiply by EI plus 25. That is your VA. And MAB, you multiply that way. This plus 75. I hope you see the point, and eventually you are able to solve your problem. So the first assignment I'm going to give you to make sure the point sinks in is look for the value of steel. Okay, let me see. The value of steel, E for steel, let's say is 205 kilonewton per millimeter squared. That is your value of steel. Please, because I'm not going to repeat this, if you are taking a photo or whatever, this is the assignment, and it's good for you. So I don't want to hear after this, oh, Mwalimu sent me this. No, this is the assignment, and I've tried to explain. And also, if there's a question, please, when you're on site, you can ask. I believe it will be easier to explain. And so, and let's say the thing is circular. Let's say it's circular, and of diameter what now? Let's see. Say the say circular a tube is made of steel, and the no, let's say, okay, let's say for argument's sake is 400 millimeter by 200. This is some 200 by 400. Which one is which? Yeah, okay, 200 by 400. Sorry, 200 millimeter by 400. Okay, let me spell it out because students will still ask questions. Now the E is here. This dimension can help you get the I. So you can substitute here and get BA in terms of in the actual values. Then you put here, then you're able to solve for VA, BMA, BV, and also and so on. Just to make sure the point sinks in, unless there's a question, class rep or anyone else.